Part B, growth functions. So now we want to compare two algorithms. We want to know which one is better, which one is worse. Last time, remember when we solved that element uniqueness problem, we used two different methods, method one, method two. Yeah. How can we tell which one is faster? So we need to answer this question. Yeah. So in this part, we use a concept called a growth function concept. So when we compare two growth functions, we will explore mathematically which one in the long run it is faster. Yeah, so we compare when the problem size is very large. Yeah. Why we don't worry about the problem size relatively small? We don't worry about that part because our computer is very powerful. Yeah, so we can handle problem sizes relatively small easily. Yeah, but when the problem size become extremely large, we may have problems. Even you have very powerful computers, you cannot handle the computation. Yeah, for that reason, so let's study algorithm efficiencies. Especially we want to consider when the problem size is very large. All right, B.1, introduce growth functions. So what's the definition of growth functions? Yeah. All right. So to give a good definition for the growth functions, so let's start with formulas relationship between running time. We can treat it as a function, right? Running time function. Given a problem size, what is the running time with respect to your computer? Yeah, because running time or response time always depends on your computer. Yeah. So we need to consider that factor. Yeah. Another, number of basic operations. This quantity does not rely on your computer. For all those different computers, this number always the same. So these two measures are quite different. So, but we want to see their relationship. Yeah. So let's look at this question. First, notations. For the running time, we use this function, T of n, capital T, T of n, and the problem size. So first function. Second function, number of basic operations. So we count the number of basic operations. So we use this capital C function, C of n. Okay. So how can we connect these two functions? So we like to have some formula to connect these two functions. Okay. All right. Yeah, the basic operation. So we learned before, yeah, the operation contributing the most to the total running time. Yeah. Yeah. All right, so we have no problem. Yeah. Then another special constant we need to use in order to connect these two functions. So this constant is the execution time of a basic operation on your computer, on each individual computer. If you just do one basic operation. What is the execution time? That is a constant. Okay? Although that constant on different computers could be different, but on each one, it is a constant. Okay? It is a constant. So we use that one, little c up, okay, basic operation, as the constant. Then we can connect these two functions using some approximation formula. T of n approximately equal to little c up times capital C of n. Okay, yeah. All right. All right. Proportional, yeah. So the relationship between these two, we only use one constant, special constant, we can connect these two functions. So they are proportional. All right, yeah. So that's the relationship. All right. And so here you can see one measure, here, one formula connects two measures. The first measure we treat as non-stable. Yeah, T of n, response time. It's not a stable measure. So you cannot use that function value to compare algorithms on different machines. Yeah. But the second one is stable. Yeah. Second one is stable. Yeah. So we like to use that stable measure. But you can see in this formula, they are connected. But this little constant, you need to be aware of. Yeah. On different machines, it's a different number. Okay, all right. So then the next step, we want to simplify our formulation. Because when we write many different formulas, sometimes the formulas could be very complicated. Sometimes our formulas could be quite long, very complicated. For comparison, yeah, we want to compare relatively simple formulas. So we want to simplify complex formulas. So we take this approach here, ignore unnecessary details. Although you have a long, complicated formula, a lot of details not important. We can ignore. We can ignore. Yeah. So this approach, this approximation approach, unnecessary details, we want to ignore to get the simplest expressions, but that expressions can reflect the original function quite well. Yeah. So in order to help you understand this approach, yeah, because it looks like later you will see, it looks like we ignore a lot of things. We ignore a lot of things. How can you get comfortable by ignoring so many things? Yeah. All right. Here, we use two steps to simplify our formulas, 2 steps. All right. The first step, if a formula has many terms, usually a formula has many terms, okay? Yeah. We only keep the dominant term. That's the first step, dominant term concept. One term dominates all the other terms. If you can find such dominant term, then you can do your first round simplification. Only take the dominant term. Okay? Yeah. All right. Here, let me explain a little bit about the dominant term. All right. This one. All right. All right. First round simplification. Dominant term. All right. So remember last time we did, when we count the number of multiplications, we get a formula, right? Yeah, like this. Yeah. In the polynomial evaluation problem, when we count the number of multiplications in our first method, we use this many multiplications. If we write it out in 2 terms, these 2 terms, now you can see one term is dominant. One term is dominant. The first one is dominant. Dominant is. Yeah. Yeah. So our first round approximation, can we just take the first term to represent the whole function? We ignore the second term. So we treat the second term as the minor term, so we want to ignore it. If you ignore it, definitely we do approximation, but how much you throw it away? How much percent? How much you throw it away? Let's look at this question. It depends on the problem size and how large is the problem size, right? Yeah. When the problem size is very large, the percentage you throw away is very small, right? But when the problem size is relatively small, then that percentage will be higher. Yeah. All right. Remember at the beginning, I talked about the problem size. We mainly worry about a large problem size. We do not worry about the relatively small problem sizes. Yeah. So we focus on this n variable very large. Now you want to, yeah, so here, in order to do comparison, because we drop the second term. So we want to see how much we throw away. All right, yeah. Let's use the second term over the first term and look at the ratio. It's 1 over n. How about that? The ratio of the second term over the first term, it is 1 over n. You can see this fraction related to the number n. When n is 100, you approximately throw away 1%, right? 1%. Yeah. Yeah. Actually slightly less than 1%, but let's just use approximate number 1%. But when n equals 1,000, 0.1%, right? When n equals 10,000, you throw away 0.01%. Okay? Do you feel comfortable when you throw away 0.01%? You do not have problem, right? No. No. So here I try to convince you. When we ignore minor terms, don't worry. Yes. Yeah. We're fine. Yeah. So, yeah. Because when n equals 10,000, we do not treat 10,000 as a very large number, right? Yeah. In our computation, we do not treat 10,000 as a very large number. Okay. Yeah. So here you can see we only keep the dominant term. We get the main part. Yeah. Yeah. All right. That's the first round approximation. Okay, first round. And after that, the first round, we simplify the formula a lot. Here, we only have 2 terms. Think about it, you have 10 terms. You have 10 terms. We only keep the dominant term. We throw away remaining 9 terms. Much simpler. Yeah. So that's the first round simplification. Then the second round. Now let's do the second round. The second round. Here, this dominant term still, it has a 1/2 constant. Leading constant. So we call it leading constant 1/2. Yeah. So we want to think about if this 1/2 constant, how important it is. How important it is. Yeah. Leading constant, we know when this number larger, the whole term, the value larger. Yeah, we know the value change could be big, right? The value change could be big. All right. But this time, we look at this question from another point of view. So this point of view, we want to look at the function growth rate. How fast this function can grow. Growth. Yeah. How fast. We want to look from that point of view. Yeah. So to see that. Yeah. Yeah. Here. All right. Yeah. Yeah. So the first round. Yeah. All right. So then the second round. Now let's move to the second round. Yeah. So here, this is the second round. Simplification. Okay. Second round simplification. All right. Yeah. This time, let's consider this ratio. Yeah. This ratio, when we double the problem size, T up to n, when we double the problem size. So we should get a larger function value, right? So the larger one over the smaller before we double the problem size, T up to n over T of n. Yeah. The other side, C of 2n over C of n. So you can see the original little C of cancel out. Yeah. Here, there is a cancellation. Cancellation. That little C of is cancel out. When we do the ratio, numerator, denominator, no, we cancel it out. Yeah. That means the value of this little c constant is not important in this ratio. If you just compare the ratio, you will just compare this ratio. That little constant is not important. But this ratio can tell us how fast a function grows. If the ratio is bigger, it grows faster. Smaller, grows slower, right? Yeah. Every time you double the problem size, the ratio of two function values is larger, so you can imagine function grows faster. Okay, so you look at from that point of view, we do our second round simplification. That is, ignore the leading constant. So this round, so we can ignore the leading constant. All right, yeah. Yeah. Because it's enough to allow us to see how fast the function grows. We just take that, okay? All right. So then, after these two round simplification, we get our new concept, growth function concept. So that function is called the growth function after two rounds simplifications.
The one at bottom is which one's called the growth function?
Yeah. So for this one, for example, this example, the growth function is n squared. Okay. Yep. Drop that 1/2. Yeah. N squared. Okay. Yeah. Growth. Yep. From this name, we want to see how fast it grows. How fast it grows. Okay. Yep. All right. Yep. All right. So now, this growth function concept. Okay. Yeah. Major term, that major term, dominant term. All right. Yeah. So we take that dominant term. All right. Then, yeah, so here I give you another example. So for in our selection sort, this is the capital C of n, right? Yeah. So this is our capital C of n, okay? All right. So we can expand in two terms. The first one, the dominant term, all right? So we take this term first, but we have a leading coefficient 1/2. Yep. So our second round, we can, drop this leading coefficient. Yeah, yeah, yeah. So here, our dominant term contains the leading coefficient. Yeah. So, yeah. All right. Yeah. So yeah. So here in our previous example, actually we did that, right? Yeah. Yeah. The limit ratio, limit. Yeah. So here I use the larger term over the smaller term. That limit is infinity. Okay, infinity. This also tells us the first term, how the first term dominates the second term. Ratio infinity when n approaches infinity. Yeah. So that's the reason we call it dominant term. All right. Yeah. So then the growth function, we drop that leading coefficient. We get the growth function. All right. Yeah. So after this definition, next step, we want to see how to use this concept. So now you understand the concept. But we want to know how to use this concept. We compare two growth functions. When we compare two algorithms, our goal, comparing two algorithms. But how do we compare two algorithms? Now, after our simplification, we just compare their corresponding growth functions. That's enough. By comparing their growth functions, we can see which one is faster, which one is slower. Okay? Yeah. That's the idea. Yeah. All right. B.2, compare two growth functions. Yeah. So I use a simple example to show you how to compare two growth functions. The example, I just used that element uniqueness problem. That one, we get two methods, right? And we get C functions, capital C functions for those two methods. So now let's do the comparison. First, we get their growth functions. Second, then we compare which one is faster, which one is slower. Okay. All right. Compare two growth functions. Which method is better? Our first method, remember, we do global comparisons without doing data organization step. That's the first method. And the worst case function, efficiency function is this one. Right? This one, you know, the growth function, n squared, right? Yeah. But the method two steps. The first step, we need to sort the whole array. To do that, we need to pay this much cost. This is the cost for sorting. Okay, yeah. Remember, that is the sorting cost. Data organization, organizing data in ascending order. Then the second part for adjacent comparisons, right? We only do adjacent comparisons. Yeah. The first one, we do global comparisons. So here you can see this number comes from the global comparisons. This number comes from local comparisons. Local, but actually, yeah, because local, we can have different meaning, right? Adjacent. Yeah. Even stronger than ordinary local. Adjacent comparisons. Right? Yeah. So those two methods. All right. Next, we need to extract their corresponding growth functions based on our two-round simplification, that approach. So the first one gives us n squared. Growth function for the first method, n squared. Yeah. The second one, n log n. Yeah. N log n. N times log n. Yeah. All right. Yeah, here. Yeah, you may ask me when I use log n log n. Yeah. Because here, what's the meaning of that? What is the log base you use here? Right? Yeah, because when you talk about logarithm function, you need to give the log base, right? Yeah. Here. Yeah. In math, people, it's very common, people use log base 10, right? Yeah, because we use decimal system, log base 10, commonly used. Yeah. But in calculus, we use log base E, right? E, natural. natural logarithms, log base e. But in our computer science, the most frequently log base is 2, binary system. Our main system is the binary system, not the decimal system. So if you see LG, yeah, LG, okay? In math, LG means base 10. In CS, LG means base 2. Right? Yeah. By default. Okay? By default. All right. Now here I use LOG. I didn't specify any log base here. Usually it means the specific log base is not important. The reason we do not specify, it's not that important. All right. So here there is a hidden log base. Hidden log base. So here we assume there is a log base A. This A we do not specify, but this A here we want it greater than 1. A greater than 1. Okay? Yeah. That's the only requirement. Otherwise, if A less than 1, then this log function becomes a negative function. So we don't want to use a negative function. Okay? Yeah. So when A greater than 1, we know it is a positive function, because our growth function always positive. Okay? Yeah. So that's the only requirement. All right. Next, let's compare the ratio of these two growth functions. Yeah. All right. We use limit to do comparison. Yeah. The reason obvious. Look at the limit. When n goes to infinity, that matches our consideration. We want to focus on the problem size very large, right? Yeah. So the trend reflected when n approaches infinity, it tells us what we really want to know when the problem size becomes very large. Okay, yeah, n goes to infinity. We want to see the trend. Okay, yeah. All right, so we take this ratio, then find the limit. Let's do the simplification first. Yeah. We cancel out common factor n. After simplification, we get this limit. N over log n. N over log n. Can you see this limit? What is this limit? Recall from your calculus knowledge. You need to, bring back your calculus, finding the limit, that knowledge. Okay, yeah. So I already explained that we use log base a greater than 1. Yeah, that limit is infinity. That limit is infinity. Okay, yeah. Why is that? Why it is infinity? Yeah. Why is it infinity? All right, yeah. The first way to see it, yeah, so we want to understand, we want to understand. Why is that? Yeah. Because for this class, it is important. Compare n and log n. How much is the difference? This question is important for this class. Yeah. So we are willing to spend some time to understand their difference. Before we go to the discussion. Before we go there, go to discussion, I like to give you some simple examples that you feel about the difference of these two functions, n and the log n. Okay, all right. But here, for convenience, I like to choose a equals 2. Yeah. So in our computer science, the most commonly used log base 2. Yeah. So here, let's use a equals 2. Okay, all right. Then log base 2, yeah. Let's consider n equals 1024. You know this number, right? You're familiar with this number, right? 2 to the power of 10. All right. All right. 2 to the power of 10. All right. Then this ratio, you can see that function ratio, and over this time, we take a log base 2. We get over 10, right? Over 10. Okay. Greater than 100, right? The ratio greater than 100. Okay. So you see the difference of these two functions. Let's try another one. All right. Approximately 1 million. How about that? $1 million. Approximately 1 million. Yeah, we use approximation. Okay. Yeah. All right. Because this number approximates 1,000, right? It's a good approximation, 1,000. So 1 million approximately equal to this number square, right? 2 to the 10th squared. 1,000 squared is 1 million. So 2 to the 10th squared, 2 to the 20th. Sorry, 2 to the power of 20. Okay, all right. Now this time, n over log of n is approximately, yeah, let's use approximate equal. Yeah. 1 million over 20. How about that? How about that? 1 million over 20. Okay. Simplification, right? And 5 what? So 1. 50,000. 50,000. Okay. Yeah, you see, the ratio is very big, right? When n grows, the ratio grows very fast. Look at that. Yeah. But that's just from numbers. Okay. From math, we can also see the limit is infinity. Limit is infinity. Okay. Yeah. All right. The first way, we can use variable substitution. Yeah. Because logarithm, usually people are not quite familiar with the logarithm, right? Yes. So we want to replace that log function by a new variable. Substitution, variable substitution. So we take u equals log of n. Yeah. All right, here. U equals log base a of n. Okay, yeah. Then n equals a to the u. Okay, all right. Now, when we look at this limit, we just get a to the u over u. A to the u, it is an exponential function. The base a, the base A is greater than 1. Yeah, so base A is greater than 1. Okay, and we know exponential function dominates any polynomial, right? Exponential function dominates any polynomial. Here, U just a linear polynomial. Yeah, linear polynomial. So definitely A to the U dominates. All right. So that's by our knowledge from our real world life, right? Yeah. Knowledge. Yeah. But mathematically, we can also prove it. Mathematically, why it is correct mathematically. Okay? We can also prove it. Yeah. Because these two functions, comparing these two functions, also very important for this class. Also very important. So we're willing to spend some time to understand it better here. So our next step, we want to rigorously prove it is correct. Rigorously prove it. All right, so our next step. So we need to use a powerful math tool. It is called a L'Hopital's rule. L'Hopital's rule. A powerful math tool for calculating limits. When you calculate limits, this rule is very powerful. Here, I want to show you. All right, method 2. Use L'Hopital's rule to calculate the limits. All right. The situation to use this L'Hopital's rule when we calculate the limit of ratio of two functions. That what we are doing here, right? Ratio of two growth functions. So that's the typical situation for the L'Hopital's rule. Okay, all right. Many times when we calculate the limits of ratio of two growth functions directly, it is very hard. Then L'Hopital's rule tells us, you just calculate the derivatives, the ratio of their corresponding derivatives. The same thing. This ratio, these two ratios are the same. But you need to check, there is some condition. You need to, before you apply L'Hopital's rule, you need to check if the condition is right or not. If the condition is right, then you can safely apply the L'Hopital's rule. If it's not, don't apply it. It's wrong. Yeah. So what's that condition? The condition is that ratio should be this form called an indeterminate form. Indeterminate form. What's the indeterminate form? Here, here I give you two indeterminate form. The first one is infinity over infinity. Second one is the second one is 0 over 0. If some of you has the knowledge in calculus, yeah. So, but here I do not require you, you know. But here, if you happen to know it, yeah. I just talk about this indeterminate form. Yeah, infinity over infinity. Here, that's the form. All right. That's not we really want to calculate infinity over infinity. No, nobody can calculate infinity over infinity. Okay, so this just represents some special form. Ratio of two functions. The numerator function approaches to infinity. The denominator function also approaches to infinity. So infinity over infinity. That's the meaning. Okay. Yeah. But you can think about why we call this form indeterminate form. Infinity over infinity could be anything, right? Could be anything. Could be a small number, could be a large number. Think about that. Could be constant, could be nothing, all right? Yeah, that's why indeterminate. Because you do not know what it is. That's what we call indeterminate form, okay? So you check that first. For this class, we won't have the 0 over 0 case, because our growth function always infinity over infinity. Okay, you just check if it's infinity over infinity form. If it is, then you can safely apply the L'Hopital's law. All right. Here we have infinity over infinity, a to the u exponential function. When a is greater than 1, it goes to infinity. All right, yeah. So we can safely apply L'Hopital's rule directly here. Okay. You need to take derivative of the numerator, derivative of the denominator. Okay. Yeah. Here, derivative of a to the u. So you can find it from web, from your old textbook, calculus book, whatever. Yeah. Or search the web derivative. Yeah. That's natural log of a times a to the u. Denominator derivative, just 1. Denominator. Okay. Yeah. Yeah. Here, denominator, we use the power rule. In derivative, there is a power rule. Okay. Power rule for derivative. When you have a power function, okay, yeah, x to the, yeah, you know, to some number, yeah, here, yeah, let me use r, okay, yeah, power function, yeah, but here this exponent r, not necessary integer, all right, not necessary integer, okay, yeah, all right, r, yeah. Real number, yeah, so you can treat as a real number, all right, real number, right? The power rule tells us its derivative, prime derivative, equals r times x to the r minus 1. Okay, that's the power rule. Okay, power rule. Yeah. Here we apply the power rule, just 1. You treat u as x, variable u. Okay. Yeah. Power rule by power rule, that's 1. All right. Now this ratio, denominator is 1, numerator goes to infinity, right? Yeah. So by the L'Hopital's rule, you get the answer infinity. You get the answer infinity. Okay? Yeah. Here I show you how to use L'Hopital's rule to calculate the limit of 2 functions. First example. All right. Yeah. All right. Yeah. But here, another thing. Yeah, here. I said we want to do this kind of calculation rigorously. Yeah, rigorously. Yeah. Here, to do it rigorously. Yeah. What's the idea? We consider continuous variable. Yeah. So let me talk about this question. Continuous variable. What do you mean continuous variable? Let's look at this question. Our original one, finding the limit n approaches infinity n over log n, log base a of n. Let's consider this question. It's also, this form is also the indeterminate form, right? Yeah. Infinity over infinity form. So we can apply the L'Hopital's rule, right? By the condition, we can apply the L'Hopital's rule. But here, there is another important question you need to be aware of before you apply the L'Hopital's rule. So what's that? L'Hopital's rule, you need to calculate the derivatives. But here, these two functions, n and the log of n, our variables, our variable m, it's a discrete variable, right? So this variable, we call it discrete variable. Discrete variable, not continuous variable, right? Not continuous variable. Not value changes continuously, right? There is no gap. Discrete variable, value changes 1, 2, 3, discrete values. You cannot take any value between 1 and 2. So it's not continuously changed. Discretely changed. Okay? Yeah. For discrete variables, the derivative is not defined. You cannot define derivatives if you use discrete variables. Okay? Yeah. You cannot. The derivative is not defined. Yeah. So in order to solve this technical question, we need to convert this function to a form using continuous variable. We need to do that conversion first. Before we apply the L'Hopital's rule, let's do that conversion first. Conversion to the form using continuous variable. All right, so let's do this step first. All right, yeah. This is the continuous version. Look at that. This is the continuous version. Right? Yeah. We replace n by x. Our x can change continuously. Okay? Yeah. Log of n, we replace it by log of x. X can change continuously. Okay? Yeah. After this change, we can apply L'Hopital's rule safely, right? Derivatives are well defined. This time we can take derivatives. Otherwise, if you take derivative, it's not defined. You cannot take derivatives. Okay? Yeah. All right. All right. So then, let's apply L'Hopital's rule. Yeah. Because this form is infinity over infinity. So no problem. We can do it. Yeah. Derivative of numerator by the power rule here. Power rule, it's 1. Okay, it's 1. Derivative of denominator log function, log base a. Yeah. So we can find this formula somewhere. Yeah. All right. So 1 over natural log of a times x. Formula. Then we do simplification. After simplification, constant natural log of a, it's a positive number. This is a positive number. Because a greater than 1, it's positive. Okay? Positive number, positive constant. Then x goes to infinity, so this number also goes to infinity. Yeah. So we find this limit goes to infinity. After that, then we need to get back to the original limit, right? Because our goal is this limit. Okay, we need to do some interpretation to get back to the original limit. So from this limit, can we make our conclusion on the original limit? Another question. Our last question to answer. Here. We want to make conclusion, but you need to explain why after you get this continuous variable version limit, then you can make a conclusion on discrete variable version. You need to explain that. You need to explain this step jump is legal. It's legal. You need to justify it. Okay? Yeah. Our last step, justify it. All right. To understand this step, you need to understand how do we define the limit concept. You know the limit concept. In calculus, it's an important concept. Limit concept. Limit. Some function has a limit. Okay? Some function has a limit. So here we have a function goes to infinity, limit. When x approaches here, when x approaches limit, infinity. All right. So when you look at this, do you know, here, I like you to focus on this place. Focus on this place. Here, when we say x approaches to infinity, do you know in what way x approaches to infinity? Do you know that? In what specific way? Because you can make x in so many different ways, right? How do you know which way approaches to infinity? Do you know that? Right? Yeah. Because here, based on the condition here, we only need x approaches to infinity. That's the only thing we need. But how does it approach to infinity? Do you know that details? It does not say that. How does x approaches to infinity? Nobody talks about it. Okay? Yeah. X approaches to infinity. How? Yeah, here. Our question is how to approach to infinity, right? Yeah. Okay. There are millions of different ways. Think about that. Okay. Yeah, let me show you just a few of them. All right. 1.1, 2.1, 3.1, 100.1, and so on. Is it okay? Approaches to infinity in this pattern, right? This is one special pattern. All right. Another one, 1 square, 2 square, 3 square, 100 square. Is it okay? Approaches to infinity in squares. A different pattern based on the definition of our limit. Any pattern is okay. Okay? If only you approach to infinity. That's the only condition. Any pattern, no problem. Legal, any pattern is legal if only it leads to infinity. All right? Yeah. All right. Now, based on that understanding, can we take a special pattern here? Can we take special pattern here? Natural numbers 1, 2, 3, 4. Natural numbers. Can we take these natural numbers? 1, 2, 3, 4, 5. If you take, that's discrete variables, right? Yeah, that's legal. We can do that. We just take natural numbers. So we get a result for the discrete function ratio. Legal. Legal. Now, here you can see I spent a lot of time to explain rigorously. You get the answer, but in the right way. Some students frequently, they only care about the final answers. Yeah, that's quite common. So even the derivation could be wrong, yeah, or not completely right. Yeah, they only care about the final answer. Yeah. But here we want to make sure our derivation procedure also correct. All right. Yeah. Now, at this point, this approach, you can see we do continuous variable version, then back to the discrete variable. This approach is quite different from our textbook. If you read a textbook, you should be careful here. Our textbook does not do that continuous variable part. It just works on the discrete variable directly. Then there is a hole because the derivatives do not exist for discrete variables. Okay, there is a hole there. All right, yeah. So be careful when you read the textbook. All right, any question? Yeah. All right.
How does the growth function n log n faster? The one on the bottom.
Right, n log n faster, yeah, because faster here because this function value is smaller, right? When you take the bottom one, outgrow the top one, right? Outgrow. If you grow faster, the algorithm is slower, right? Because that number represents the counting number, counting function. The number of operations larger, that means your algorithm is slower. Think about the opposite. Yeah. The function grows faster, that means your algorithm is slower. The function grows slower, that means your algorithm faster. Just opposite. The trend, opposite. Yeah. Good. Yeah. All right. Yeah. All right. Next. Yeah. I've about 10 minutes. Let me see. Yeah. Less than 10 minutes. I want to explain one question in the project 1. Yeah. Project 1, remember, when we get around that overflow problem, last time I explained the overflow problem. Yeah, because it's not easy to detect it. Yeah. Sometimes, even if it occurs, we don't know. We cannot see any sign. Yeah. In order to, avoid that, sometimes you need to do your operation carefully. After each operation, you need to check if it's correct. Sometimes. Yeah, all right. But here, we don't want to do that. Yeah, we don't want to check every time. Every time when we do one operation, we check if there is overflow. Yeah, there is a way to check it. Yeah, if you search the web, there is some way to check it. Okay, if the operation causes overflow or not. Okay, yeah. But in our project, we don't want to do that. We want to find a way it never causes overflow. Okay? The overflow won't happen. Won't happen. All right? Yeah. So here in Java, we use this big integer class. Big integer class. It uses some special operations to avoid overflow. Why? Yeah. Why? So here I want to explain why. First, it does not use the regular integer. We know regular integer, you have to use certain number of bytes. Long integer, 8 bytes. Certain number of bytes for regular integers. Then there is a limit. Here, we don't want a limit. Here, when we define an integer, we don't want to put any limit on it. So how to do it? A smart way, using string to build your unlimited integer. String, we know a string has no limit, right? When you represent a string, there is no limit for the number of characters, right? Any number is legal, okay, for string. Yeah. So then they just build big integer on top of string representation of integer. Double quotes is digit numbers, double quotes. You make it a string. After you make it a string, no limit on digits. That's pretty smart, simple and smart. Unlimited, millions of digits, fine. Billions of digits, fine. Yeah. The problem, probably too slow. Yeah. That's another issue, right? Computing time too slow. That's another time. Yeah. But conceptually, it's legal. Okay. All right. After that, so this is the beginning of your constructor. After that, there is another constructor here. Yes, last time one student asked me about the random number generator. Yeah, because for this project, you need to generate random numbers for your data, right? Coefficients and a variable. Here, this constructor, random generator. You specify the number of bits, okay? Yeah. The size, all right? The size, yeah. How large you want your integer, yeah. You can specify that. Then, this random object, you put a random object there, all right? Yeah. So here, this is a random object, right? Yeah. So then you construct big integer. Yeah. So that random object can help you generate the random number you need. Yeah. You just find some simple examples on web. Okay. Yeah. Find a simple example on web using this constructor to generate random big integers. Pretty straightforward. Pretty straightforward. Yeah. After that, you get all your data. Okay. Coefficients, X value. Yeah. You get all you need. Okay. Yeah. Then when you do operation addition, because we only do addition and multiplication. Okay. Addition, you need to do not use a plus sign, use dot add method. Okay. Dot add method. Multiplication, do not use that star operator, use this multiply method. Okay. Yeah. You need to write a little more. Yeah. Yeah, it's okay. Write a little more, but the overflow is gone. Okay. The overflow is gone. Even your answer has thousands of digits, no problem. Yeah. When you do your experiment, the second experiment, the first time I asked you to do a small data values. Yeah, because we want to check they're correct. Okay, so you apply it on small data values. The second time, you need to apply on big data values because we want to compare the time difference for the second one. The first one, I want to experience the response time is quite slow. Okay, yeah, try to get longer than 10 seconds. Yeah, but less than 30 seconds. Yeah, not too long, because you don't want to wait too long, right? If it's longer than 10 seconds, you already feel it's quite long. 10 seconds. Yeah. So you compare the second one, you will see. Yeah. When you print out the answer, very long. Okay? So the screen, very long. Yeah. All right, so that's the project. Check, yeah. So technically, I think you can do it. Okay, after you understand all these things. Yeah. So now technically you can do it. All right, so that's it.